Hello everyone and welcome back to your YouTube channel and welcome to this fantastic video of today. As you must be aware, I am working in this brand new module that is called Data Analytic for Smart Energy Systems. And one very important aspect in this course is that you must understand the models related to the energy system. When we are working with electricity systems, a very important aspect is dealing with power electronic converters. And those power electronic converters, they can create some distortions in the electrical signals as voltage or currents. And those disturbances, we use the name harmonics. So the job today is I will show you some calculations related to harmonics in AC signals, and in particular we are talking about voltage, currents, and power. So without further delay, let's start by reading this statement over here. A specific power electronic converter is connected to a 230 volts supply. It's known that the converter demands electrical active power of 750 watts and a power factor that is 0.952 at a rate frequency of 50 hertz. So this data over here, 230 volts, 750 watts, and this power factor over here, all of them are defined at fundamental frequency, rate frequency of 50 hertz. However, it's known that there is a harmonic distortion, in this case in the current signal, and the current has a total harmonic distortion that is 37.2%. So what I am telling you is that we clearly know that there is a harmonic distortion, and the global indicator for that is the THD, total harmonic distortion, and in this very specific case, this is 37.2. So there are several questions over here. The first one is calculate the magnitude of the complex or apparent power. In this case, the units volt amps. Then calculate the reactive power Q. Again, in this case, the units is volt amp reactive. And this is at 50 hertz frequency. Then calculate the RMS value of the current at fundamental frequency. Then the magnitude of the harmonic current component. Then finally, the last question is the RMS current amplitude when we are considering the harmonic distortion. Okay, so again, we are using here MATLAB Live Script. MATLAB Live Script allows us to focus more into the explanation instead of the calculations, because we can use the classical MATLAB coding for obtaining the numerical results, okay? So let's start here. As you can see, initially we are defining here the active power, 750. We are defining the power factor 0.952. The magnitude of the voltage is 230 volts. And the total harmonic distortion is 0.372. Remember, we don't use the percentages when we are working with the numerical values. So here is 0.372. Okay? Perfect. The first step is to calculate the magnitude of the complex or apparent power. To do that is very, very simple. We can divide the active power P, that we already know is 750 watts, divide by the power factor at 50 hertz, and we already know that that is 0.952. So when we put the number together, we have here the magnitude of the apparent power, and as you can see, the numerical value is 787.8 volt amps. The next step is to calculate the reactive power. Remember Q, and Q can be obtained from the very interesting and amazing property of the power triangle. So from the power triangle, we can obtain that the reactive power will be the square root of this difference over here, the square of the apparent power minus the square of the active power. In other words, we are calculating the square root of the 787 volt amps square minus the square value of 750 watts square. So when we put the number together, we have here the amazing reactive power and numerically equal to 241.1 volt amps. Now the interesting part, we can obtain the fundamental frequency current, RMS value of the fundamental frequency, and because we know already that the apparent power here is 787, and that is at the supply frequency 50 hertz. So dividing the apparent power 787 by the rate voltage, and that is equivalent to 230 volts, we obtain that the current at the rate frequency, in this case, the rate frequency is 50 hertz. So we obtain over here that the RMS current at 50 hertz is 3.43 amps, okay? Next step is we know that the current that is coming from the supply is having harmonic distortion, and we know that that harmonic distortion is 37.2%. So what we want to obtain is the harmonic current component, and that can be obtained multiplying the THD, the total harmonic distortion, by the RMS current at fundamental frequency. So when we multiply here 3.43 by the THD, in this case 0.37, we obtain that the harmonic current component is 1.27 amps. Finally, and the final very interesting question is related to the RMS current, but in this case, including the harmonic distortion. So we can obtain the current, the RMS value of the current, including the harmonics, by combining here the square root of the square value of 50 and the harmonic components. So we are substituting here 50 hertz RMS value is 3.42. The harmonic components is 1.27. So finally, and there is no surprise, the RMS value of the current, including the harmonic distortion, is 3.62 amps. So as you can see, fundamental frequency current is 3.43, but when we include the harmonic distortion, the RMS value increased to 365. So as you can see over here, the effect of adding those harmonics into the current is increasing the total RMS value. So here today we learned something about harmonic calculations in AC steady-state systems. We calculate the current with harmonics and the fundamental current, and we are reaching the end of this video. I hope you enjoyed this video. If yes, please be part of the community. Subscribe to LinkedIn in order to get more information about what we are doing in terms of research and development. Also, be part of the community in YouTube. Subscribe to the YouTube channel to get more information about the coming videos and activities. And finally, there are a couple links over here for our social media, Twitter, former Twitter, today called X, and also Instagram. Well, we are reaching the end of this video. Thank you very much for watching, and I will see you at the next one. And it's time to say the very classic bye now.